Hello everyone, welcome back. Now we are gonna we're gonna cover our second topic, which is Archimedes Principle. So topic number 2 is Archimedes Principle. And as I stated before, this basically is about buoyant force. So let me ask you this. Have you ever noticed that when you jump into the pool, you feel lighter? Okay, and why do you feel lighter? And you probably also have seen that if you try to push a balloon into the water, it actually comes up to the surface. Okay, so for example, if we put a balloon inside the water and leave it, and let's say initially it's at zero velocity, and it's staying at zero, and then when I leave it starts accelerating upward. The gravitational force is downward, but why does it accelerate upward? It means there must be some other force acting on this which is actually stronger than the gravitational force, and therefore the net force is upward, and this object then pops up to the surface. Okay, and this force, that other force, is actually called the buoyant force. Anytime you insert an object inside a fluid, it experiences an additional force, and that force is called buoyant force, and that force is always opposite to gravitational force. So the gravitational force is downward, this additional force is upward. Okay, so let's draw a picture. Just 1 second. Okay, so imagine this object is a container and is filled with fluid. So this is the surface of the fluid, and I insert some object. Let's, for simplicity, assume this object is a cube. Okay, it doesn't need to be cube, it can be any shape, but just for simplicity. Now we have seen before that the pressure inside a fluid changes with depth. This top surface here is at lower depth. Okay, so for example, the top surface is at this depth, and the bottom surface is at a larger depth. So because it's inside a fluid, the fluid exerts a force. Okay, so there will be force here called this F1, which will be equal to pressure 1, pressure at this level, times the cross-section area of the face of this cube. Let's call it A. So that's the area of the face of this cube. So that's the total force being exerted by the fluid downward at the top surface. There will be a force on the bottom surface, okay, and that force will be upward, because a fluid always exerts a force perpendicular to the surface. Okay, now this force will be at the bottom, F2, which will be the pressure at the bottom, which will be, let's say, call it P2, times the cross-section area. Now because I have assumed that this is a cube, each face has the same area, so this area will also be A. Okay, so we see that because P2 is larger than P1, it follows that F2 is larger than F1 in magnitude. So it means this net upward force, and this really basically is due to the pressure difference. Okay, so there will be net force. Let's say this is F2 and this is F1. That's the force at the top, and if we add these two forces as vectors, we get the net force, which will be this much, and this will be F up, and this is called F buoyant. Okay. Now you may think, is there any sideways force? No, actually, on the side, the fluid is exerting pressure. For example, here the force is smaller, but as we go deeper, the force becomes larger. Okay, these are forces being exerted on this side, and on the opposite side, at the same depth, there's a force in the opposite direction, and all these forces actually cancel. All the horizontal forces cancel, and the net force is only in the vertical direction, and it's upward, and that force is due to pressure difference. Okay, now so this tells us that there will be an upward force, but how much is this force? What's the magnitude of this force? For that, we are going to go to that is what the Archimedes principle tells. Archimedes principle tells that the magnitude of this buoyant force, call this FB, so this means the magnitude, is equal to weight of the fluid displaced. Okay, so this is Archimedes principle. Now weight of the fluid displaced means, let's say if I insert an object inside a fluid, and it does not even need to be a cube, it can be any shape, and let's say that object has 1 liter of 1 liter volume. It means it displaces 1 liter of that fluid, and let's say that fluid is water, then it will displace 1 liter of water. Okay, and then that 1 liter of water will have some weight, it will have some mass, and then if you multiply that mass by g, you get the weight of that water being displaced, and that is how much the buoyant force is. Okay, so let me write this down. So weight of the displaced fluid is simply mass of the fluid which is being displaced times g. Okay, so this is F buoyant. Now when we are working with fluids, it's actually it's better to write mass in terms of volume. We know the density of any object is defined to be mass over volume. Okay, so from this it follows that mass equals rho times volume. So the mass of the fluid which is displaced is density of that fluid times the volume of that fluid which is being displaced. Volume of the fluid which is displaced is the same as the volume of the object submerged inside the fluid. It's called Vs. Okay, so let me write this down. Vs is the volume submerged, is the volume of the object actually it's better to write it slightly differently. Vs is the submerged volume of the object. Okay, so what this means is this Vs, for example, if we have some fluid and we take an object which has some volume V, and we can call this volume of object. VO means the volume of this object. We take this object and we insert into this fluid. Now for example, if we don't fully insert this, for example if we insert only up to here and only this part of this object is inserted inside the fluid, okay, only this part, then this volume submerges only this volume, this part. It's not the total volume of the object. It is only the volume which is submerged inside the fluid. Okay, so this is important to distinguish between the volume of the object and volume submerged. In the special case, when we fully submerged an object, let's say if we take this cube or whatever this shape is, if object and we fully submerge inside the fluid, in this case the volume submerged is equal volume of object. But in this case, when it's not fully submerged, then volume submerged is less than the volume of the object. Okay. So now then, going back to buoyant force, mass of the fluid which is being displaced is the density of the fluid. This is not density of the object being submerged. This is the density of the fluid times volume submerged. So then this is mf, then F buoyant becomes mf, which is now rho F times Vs times G. Okay, so this is the important equation for buoyant force. Buoyant force equals the density of the fluid times the volume submerged times G. This is how much buoyant force is, and direction is upward. Always, there's no exception. This buoyant force is always against gravity, or it's upward. Okay, and its magnitude is given by this equation. Okay, now we're going to cover a few special cases. Okay, so special case is totally submerged objects. Totally submerged object. Okay, so consider the special case when the object is fully submerged. So when it's fully submerged, then what is Vs? In this case, when it's fully submerged, Vs equal the volume of the object, because all of the volume of the object is submerged inside the fluid. Okay, so let's draw a picture once again. So this is the fluid in this container. There's this object fully submerged, and let's draw a free body diagram of this object. There are two forces acting on this object. One is the gravitational force, that is Fg, and then there is a buoyant force which is upward. Okay, so these two need not be equal in magnitude. Okay, so there are two forces in opposite directions. Okay, and we know F buoyant equals rho of fluid times the volume submerged, but here volume submerged is volume of the object. Okay, for this special case, times G. And now let's get the magnitude of the gravitational force. That is mass of the object. Okay, so MO means the total mass of the object times G. And mass of the object is same as the density of the object times the total volume of the object. Okay, so times G. Okay, so remember another equation for F equals mg is that it's rho times volume times G. So in this gravitational force, this rho naught and V naught are not the submerged. V naught is not the submerged volume, it's the total volume. Okay, so we get an expression for Fg. So this is always true, this equation. Okay, whether or not an object is submerged, the gravitational force in terms of density and volume of the object is rho times V times G. Okay, so now then let's choose some direction to be positive. Let's choose upward to be plus direction. Okay, then F net on this object is the difference between these two forces. That's upward force minus Fg. Okay, so if Fb is larger in magnitude, then this object will accelerate upward. if the buoyant force is smaller than gravitational force, then this object will accelerate downward. Okay. Okay. So F net is, and what is F net? F net is mass times acceleration. Mass of the object times acceleration. So this is equal to then FB minus FG. And mass of the object is rho of the object times the total volume of the object times A equals FB, which is rho of the fluid, times volume of the object times G, minus the gravitational force, which is rho of the object, volume of the object, times G. And nicely in this equation, volume of the object cancels. Okay. So we are basically looking for acceleration. Okay. So acceleration then equals rho of fluid minus rho of object divided by rho of object. So I just rearrange this equation, and then G is common factor. Okay, and this can simplify as rho of fluid over rho of object minus 1 times G. So this is very important equation, that acceleration is rho F over, it's the ratio of the two densities, the ratio of the fluid, density of the fluid over density of the object minus 1. Okay, times G. So this will give you the acceleration. Now consider a special case that rho fluid equals rho object. If the density of the fluid equal density of the object and the object is fully submerged, then rho fluid over rho naught equals 1. Okay, and if this is 1, then this factor becomes 0. So in this case, rho fluid over rho object minus 1 equals 0, and the acceleration is 0. And this is called as equilibrium case, because if there's no acceleration, it means the net force is 0. So we discover a very important thing, that if rho fluid equals rho naught and the object is fully submerged, then the F net equals 0 basically means that buoyant force equals the gravitational force, and they cancel each other. And because these two forces are equal, the net force is 0. It means the acceleration of the object is 0. So if it's initially going down with some initial velocity, it's going to continue going down with the same constant velocity. If it's at rest, if you submerged and it's at rest initially, when you leave it, it's just going to stay there. Okay. And as you can see, if so, this was one possibility. The second is, if rho of fluid is bigger than rho of object, in that case rho fluid over rho object is bigger than 1, and then rho fluid over rho object minus 1 is bigger than 1. Okay, from which follows the acceleration is positive. Okay, so the object accelerates upward. So what this really means is that if you submerge fully an object inside a fluid such that the density of the fluid is larger than the density of the object, then that object will have a net force upward. The buoyant force will be larger than the gravitational force on that object, and it will accelerate upward, which we chose to be plus direction. And this is the reason why, for example, if you submerged a balloon inside a fluid, inside water, the density of the balloon is much smaller than the density of the water. So the density here of the fluid is larger, and that's why it accelerates upwards and pops up to the surface. And on the other hand, if let's say you have a sphere made of steel, a steel ball, let's say, and you submerge inside that fluid, steel has much larger density than water. It will still experience an upward force, but that upward buoyant force will not be large enough to balance the gravitational force, and in that case that object will sink and it will go downward. So that is our case 3. Case 3 is if the density of the fluid is smaller than the density of the object, or the object is more dense, then rho fluid over rho naught is less than 1, and which really means that rho fluid over rho naught minus 1 is a negative number. Actually, here I should not have said that this is greater than 1. I should have said this is greater than 0. Okay, so here it means greater than 0, which means positive. Okay, yeah, so this number is positive. But if rho fluid is less than rho object, then this number is negative, or it's less than 0, and then from this it follows that acceleration is less than 0, and the object accelerates downward. Okay. Now next case is the partially submerged objects. It's usually called floating objects. So let's call this case floating objects. Or equivalently partially submerged objects. Okay. So in this case there is again this container and this object, and we take this object, again this has some volume V naught, and we submerged into this but not fully. Okay, so only part of the volume is submerged, and that volume is Vs, and which is less than Vo, the volume of the object. And this object is in equilibrium, meaning it's just resting at the surface, it's not accelerating. Okay, so it's static equilibrium basically situation. Okay, just think that you throw a toy duck in water, and it just partially submerged and just sitting there in water tub. So in this case, again, let's first draw the free body diagram. Now there's a gravitational force always there, that is always there. So Fg equals mass of the object times g, but that we can write as rho object total volume of the object times g, and then there's a gravitational force which is upward. Now what will be the magnitude of the gravitational force, of the buoyant force in this case? Now remember here the net force is 0 because it's a static equilibrium, so the total force must add up to 0, which means that the buoyant force must be equal to rho object times the volume submerged times g, that's the buoyant force. In this case, F net must be 0 with static equilibrium. Okay, So what this means is FB minus FG equals 0. So FB equals FG in magnitude, and FB is density of the object, volume of the object submerged, times G equals the gravitational force. Okay. Oh, sorry, I made one mistake here. This, for the buoyant force, this must be the density of the fluid, not the density of the object. Okay. So F buoyant should be density of the fluid. It's very important. It's not density of the object. Only for the gravitational force we use, it is the density of the object. Now G cancels in this equation from both sides, and we come up with a very important equation, that Vs, that's the volume submerged over total volume, equals density of the object over density of the fluid. So Vs over Vo, this ratio is fraction of the volume submerged. Okay, so for example, if Vs over Vo equals half, it means that half of the volume is submerged when you see submerged, and half the volume is above the surface. And okay, so this ratio is simply the fraction of the volume submerged. If this fraction is 1, it means it's totally submerged. If this fraction is 0.25, it means 25% of the volume is submerged and 75% is above the surface. And so this equation says that when some object is floating at the surface, the fraction of the volume which is submerged is simply the ratio of the densities. Is the density of the object or density of the fluid. That's what it depends on. It means if rho object becomes smaller, this fraction becomes smaller. So the object which are less dense, less percent of their volume is submerged under the surface. Okay. So this is an important equation for floating objects. And if you are asked to find the volume above the surface, volume above the surface, let's say call this V above, is simply the total volume minus the volume submerged. Okay, so this is how you can find the volume above the surface. Now let's see what's next. Okay, now we're gonna do a few examples. So I have covered the concepts. So next I have 2 or 3 examples, and we're gonna now go over these examples. Okay, so now let's consider floating ice in water. Floating ice at the surface of the water. Or you can think this is ice, frozen lake at the top, and there's some ice floating. And let's see what percent of ice is underneath the water and what percent of its volume is above the surface of water. Density of fluid, which would be here density of water, is 1000 kilogram over meter cubed. Okay, and density of object, which is ice actually is less dense than water, so here it would be, the object would be ice, and that is 917 kilogram per meter cubed. So the fraction of volume which is submerged is then simply the ratio of the density of ice over density of fluid. So density of ice is 917 kilogram over meter cube. I don't need to write in the units because they're going to cancel out. Then density of the fluid, and this is 0.917, okay, which is 91.7%. so it means 91.7% of the volume of that ice is submerged under the surface. What we see is actually only, so let's say volume 91.7%, 100 minus 100% minus this, you get 8.3%. so what we see, this percent is above the surface and 91.7% is below the surface. Okay, so what we see is just a very tiny fraction of the ice. If you see a huge iceberg floating in a lake, remember almost 92% of that volume is hidden from you. It's underneath. What you see is only about 8%. Okay, so that was example number 1. Okay, let's call this example 1. Next. Okay, so here's another example. So we have a ping pong ball. A ping pong ball has an average density of 0.08 so it's really very low density, gram per centimeter cubed, and a diameter of 3.80 centimeter. So what force would be required to keep the ball completely submerged? Submerged. Okay, so what force we need to keep it completely submerged? No, here's what this problem is really saying. To complete submerged underwater, sorry. So I need to specify which fluid. Okay, so imagine this is ping pong ball. Okay, and it's this completely submerged inside this fluid, and if I leave it, because it's a very low density, it has a buoyant force always inside the fluid, and it's a gravitational force. Okay, now because this has very low density, the gravitational force will not be large enough, and this will pop up to the surface. To keep it coming to the surface, we need to apply an additional downward force. Okay, call this force F, so that then it does not come up to the surface. Okay, and that meaning the force we need to apply will balance the downward forces and upward forces so that the net force becomes 0. So this problem is asking what is the magnitude of this force F which we need to apply. Okay. Okay, so now Let me give you a few couple of tips, unit conversion tips. 1 gram per centimeter cubed is equal to, you can do the grams to kilogram and then centimeter to meter cubed, but you can memorize this, is 1000 kilogram per meter cubed, because usually we want units in kilogram over meter cubed, the SI base units, kilogram, meter, second. So 1 gram per centimeter cubed is 1000 kilogram per meter cubed. And density of water, of pure water, is 1000 kilogram per meter cubed. So, and this is also 1 gram per centimeter cubed. So the density of water is either 1000 kilogram per meter cubed or 1 gram per centimeter cubed. Another important conversion factor which may be useful or may not be is that 1000 liter equals 1 meter cubed. Okay. So these unit conversions, I'm not sure if these are given on your formula sheet. Okay, so now let's determine this force. So we need to keep the ping pong ball coming to the surface. Okay, so the net force must be 0. So if it's in this case, let's choose upward to be plus y direction. Okay. So when we apply this additional force, then the net force becomes 0, and then F net equals 0. It means FB minus FG, and we need to apply this force downward, minus F must be equal to 0. Okay, then the force we need to apply equals FG minus FB. So that would be FB minus FG. Okay. Okay, so then we need to simplify. The buoyant force is rho of fluid times volume submerged. Now this ping pong is fully submerged, so the volume submerged equals volume of the object times G. The gravitational force is density of the object, volume of the object times G, and here V naught G is common, and we get that the force is density of the fluid minus density of the object, okay, times the volume of the object times G. And now let's plug in these numbers. Density of the fluid is 0.0840 gram per centimeter cubed. Okay, so to convert this to kilogram per meter cubed, we need to use this. Okay, so we need to basically multiply by 1000. Okay, so then we get 0.0840 times 1000. So this is actually 84 kilogram over meter cube. This is the density of the ping pong minus density. Oh, sorry. This is density of fluid. Okay, density of fluid. So that's water. That's 1000 kilogram over meter cubed minus the density of the object, which is 0.0840, and that turned out to be 84 kilogram over meter cubed. Volume of the object. Now volume of the object is pi times, so it's a sphere. So volume of a sphere is 4/3 pi times radius squared. So radius is half of 3.8 centimeter is 1.9 centimeter, and then in terms of meter, the radius is 0.019 meter cubed. Okay, so if we calculate this number, this will be the force in newtons. Let's calculate this. Okay, so if we multiply it correctly, it turns out to 0.0263 newtons. Okay, so this is how much downward force we would need to keep this ball inside, or keep it submerged. Okay, so this we're going to do one more example, and this example is really important. It's a little bit longer, but this is, I think, it's a more important example. Okay, that's example 3. Okay, let me okay, so here I took a screenshot of the problem, and hopefully you can see it. Okay, so here's the problem. So we have a circular shaped ice like a disc shape, which has thickness of 10 centimeter, and this has a radius of 60 centimeter. So we can calculate its volume, and it floats in sea, so it's basically partially submerged case. The density of the ice is this, and density of the seawater is actually not 1000, but seawater is more dense than fresh water. So part A is calculate pressure at 10 meter below the water surface. Okay, remember, pressure as a function of height equals pressure at the surface plus density of the fluid times G times H. Okay, so pressure at the surface is 1 atmosphere if it's open to atmosphere, so that is times 10 to 5 pascals. This is the pressure at the surface, times the density of the fluid, which is 1015 kilogram over meter cubed, times 9.8 meter per second squared, times the depth, which is 60 centimeters, so that is 0.60 meter. Okay, so this will be the pressure at 60 centimeter under the surface. Okay, so this will turn out to be some number. It's not important what exactly this number is. It will be some number in pascals if you just multiply these numbers out and add them. Part B. So this is part B. Let me take a screenshot of question part B. Okay, so this is part B. Okay, so this should be part B, not A. Okay, so in this thing it said there is ice, this ice cube, and some thickness, and it's partially submerged under the water surface and some of it is above. You attach a string and then you attach an iron cube, which is fully under the surface of water. It's fully submerged, and we're asked to find what's the tension in the string, and this iron cube is just in equilibrium. Okay, so this is in equilibrium. It means they are, let's draw a free body diagram of this first. So this is iron cube. There's a gravitational force, there is a buoyant force, and because there are strings, so there will also be tension force. This is the free body diagram, and all these forces must add up to 0 because this is okay, so because this is the static equilibrium, so which means that FB plus T minus FG must be equal to 0. Okay, and we are looking to find tension, so tension equals FG minus FB. Okay, so then FG is rho of the object, volume of the object, times G. F buoyant is the rho of the fluid times volume submerged, but here Vs equals Vo because there's fully submerged, times G. Okay, so this would be the tension. Again, it's we can get the common factor V. Okay, and then we get rho of object minus rho of fluid, and rho of object is the iron, that is 7,860 kilogram over meter cubed, and then rho of the fluid is sea water, and that was given to be 1,015 kilogram over meter cubed. Okay, so this would be the tension times volume of the object. It's cube, and it's each side is 10 centimeter, so 10 centimeter means 0.1 meter, so it's cube, so its volume of the object will be 0.1 cubed times 9.80 meter per second squared. So simply multiply these numbers out and you get some number in newtons, so that number will be newtons. Okay, so this would be the tension force in a string. Okay, part C, this is the last part. If the rope or the string, if the rope is cut, what is the acceleration of the iron cube? So now once the rope is cut, then the tension force basically goes away. There's no more tension force on the cube. So there's a gravitational force and there's a buoyant force. These are the only two, and the buoyant force actually will be larger because the density of the iron is larger than density of the water. Okay, so density of the iron is almost 8,000 and density of water is about 1,000. So it's gonna accelerate downward. So when we do acceleration, if we choose upward to be plus y direction, our acceleration is gonna come out to be a negative number. Okay, so then either we can use the equation we derived above. Okay, so let me see which equation. Let me scroll up. This equation, that acceleration equals. Okay, so you can either use this equation or okay, I would actually like you to derive this equation. Like start with that F net equals ma, m of the object times a, and F net equals F buoyant minus Fg equals mass of the object, which is rho of the object times volume of the object. That's mass times acceleration. F buoyant is rho fluid, volume submerged, which is VO because it's fully submerged, times G, minus gravitational force is rho object, V object, times G, equals rho object, V object times A. Okay, and here we can V object cancels, and we're gonna basically get the same equation which we already had, but I want, if you ask this question, I want you to derive this, not simply use that equation. So A equals then rho fluid minus rho object over rho object, all this times G. It's a rho object, and this actually gives you 1 minus, no sorry, rho fluid over rho object minus 1 times G. Okay, and we expect this acceleration to be negative because the density of the iron is larger. So let's plug in the numbers. So density of the fluid, which is water, which is 1015 kilogram over meter cube. In this equation, it actually does not matter which units I use for density because it's a ratio of the densities and the units are going to cancel anyways. So if you are given like grams or some other units, it wouldn't be needed if you were asked your acceleration. In this case, you wouldn't need to convert the units. So density of the fluid is, let me see that again, 1015 kilogram, and the density of the object is 7860 kilogram over meter cubed, minus 1 times 9.80 meter per second squared. And let's now calculate this number. So 1015 over minus 1 times 9.8. So you get minus 8.53 meter per second squared. So the acceleration is downward. Its magnitude will always be, if the acceleration is downward, its magnitude will always be less than g. It cannot be greater than g because the buoyant force is opposite to gravity, so it can only decrease the downward acceleration. Okay, if the acceleration turns out to be upward, then it can have any magnitude because upward force can be anything. Okay, but the downward acceleration, if it's negative number, its magnitude cannot be larger than g. Okay, so this is what its acceleration is. Okay, so this concludes my second video, and I hope these are helpful. Please, well, if you have made this far, then I'm sure you have watched these. But please, if you didn't understand any part, you can ask me during our review session on Sunday. and I am going to try to upload these on Moodle, and I hope I am able to upload these. Okay, and yeah, thank you very much, and continue studying hard for your final. And yeah, see you in a couple of days. And meanwhile, if you have any questions, send me an email and I'll be happy to answer you out. And I am getting really tired now and hungry, so it's time for me to eat something. Okay, see you guys. Bye bye for now.